Hello friends, welcome to the ATC Double Cut. My name is Micah Woods. In today's episode, I'm going to talk about a post that I wrote last week on the ATC blog, and this one is getting a double cut treatment here on the show, but it's actually a topic that I've written about quite a bit, and the reason why I've written about it so much is because people often ask me questions about this, and it's related to how the grass grows or how the grass might grow in relation to temperature combined with light. Because the paste turf growth potential, which I'm sure most people are quite familiar with, only covers temperature. The paste turf growth potential takes the average temperature, the average air temperature for a day, or for a week, or for a month, whatever time period you like to consider it for. I generally will calculate this on a daily basis and then average it over a week, or calculate it on a daily basis and average it over a month. And it converts that temperature from being either on the Fahrenheit scale or being on the Celsius scale, which is not directly related to how turfgrass might grow. And it very conveniently converts the temperature from a Celsius or Fahrenheit scale right into a percentage scale of the grass being not able to grow because of temperature, or the grass being able to grow at its most rapid potential rate based on temperature. So that's what the growth potential is. It's what I call a utility function to convert temperature from a scale on a temperature range to a scale on a percentage basis. And of course, people are very intrigued by this, and then they think about it, and then they say, wait a second, what about light? Because light also has quite an effect on how the grass can grow. And that is a very good question, and people ask me that question quite a bit. And in fact, I asked Larry Stoll about this, 15 years ago or something, maybe earlier. We've had various conversations about it, and I've tried to make calculations related to this, and I've come to the conclusion in multiple types of data analyses that I've done, I've come to the conclusion that I'm happy to just consider light and temperature separately. And so I wrote about this in the blog post, which I give a title of Light and GP Again. I wrote about this in the blog post because at some recent conferences, I have had discussions with people about whether the growth potential could be improved or adjusted to account for light. And I want to explain the key points of what's in this blog post. And I also want to perhaps say some stuff that's not in the blog post and just try to explain in plain conversational terms why I think it doesn't really help to account for light in the growth potential. As usual, I will put a direct link to this blog post in the show notes. The topic or the title is Light and GP Again. It starts off by saying a question that comes up again and again is whether the paste turf growth potential would be improved by also accounting for light. Grass growth, plant growth of any type actually, is influenced by more than temperature. The primary factors affecting plant productivity are temperature, light, leaf nitrogen content, and plant water status. So obviously, we start off by recognizing that temperature is not the only thing that affects growth. It's correct that light is going to affect growth. It's correct also that the amount of nitrogen the plant has in the leaf is going to affect growth. And largely the amount of nitrogen in the leaf, especially for C3 plants, for cool season plants, the amount of nitrogen in the leaf is going to be related to the amount of rubisco, which is the enzyme that the carbon dioxide attaches to in the first steps of photosynthesis. So the amount of rubisco in the leaf is directly related to how much nitrogen is in the leaf. So that gives an idea of how much carbon dioxide the plant can capture from the atmosphere. And also the amount of nitrogen will be correlated with how much chlorophyll is in the plant. And chlorophyll is what captures the light. So both the light capture and the carbon dioxide capture in photosynthesis are heavily influenced by the amount of nitrogen in the leaf. And that's why the amount of nitrogen in the leaf will have a controlling role in terms of the nutrients that are applied in having an effect on how much the grass will grow. So nitrogen is really important. And then the plant water status is also really important. Grass that has no water will be dormant, and grass that has plenty of water can have the potential to grow at its most rapid rate. So each one of those things, the light, the temperature, the water, and the leaf nitrogen status, those all have an effect on growth, and all of them could be completely limiting, because if we try to grow grass in the dark and don't give it any light, the grass is not going to grow at all if it never gets any light. And if the temperatures are so far from an optimum that the grass can't grow, then temperature will be completely limiting. If there's absolutely no nitrogen, then nitrogen will be completely limiting. And if there's no water, the water will be completely limiting. But this goes beyond the growth potential, and this is something that I call the EPI, which stands for Environmental Productivity Index. There's a excellent discussion of this in a couple of papers by Park Nobel. He's the author of a plant physiology book. I'll put a link to that in the show notes also. I believe the title of that is Quantitative Plant Physiology. Maybe there's a couple other words in the title, but I think one of those words is quantitative. And in that book, he works through some interesting quantities related to plant growth and to the physiological functions of plants. And he did work with cacti, and he was able to model the growth in something that he called the Environmental Productivity Index by looking at those four factors: the light, the temperature, the nitrogen, and the water. And I think if we want to realistically consider how these types of models can be used for grass growth, for turfgrass management, we need to be realistic and consider that all of those factors are involved. However, I've given seminars about this, and maybe you remember some of these, or you've stumbled across some of these slide decks or some of the old blog posts where I've talked about this. And I generally try to simplify that, because I say that there's two things that turfgrass managers cannot control out of those four. The two things that cannot be controlled are the light and the temperature, but two things are theoretically able to be managed to some extent by the turfgrass manager. Those are the nitrogen and the plant water status. And because the turfgrass manager can manage the plant water status and the turf manager can adjust the leaf nitrogen content, we can link those to the growth potential. And that's what much of the fertilizer, the types of fertilizer predictions that I make going into the future, predicting how much nitrogen the grass may use, how much the potassium requirement may be, and so on. That's based on linking the nitrogen to the temperature, because the temperature is something that cannot be controlled, but we can predict how that may affect grass growth or enable grass growth using the growth potential. and then we can simply link nitrogen to that. And that is something where the nitrogen can just be linked to the temperature. So we can simplify the environmental productivity index. But we can't simplify the environmental productivity index in terms of light because the light can't be controlled. So we're left basically with light and temperature. And that gets to the heart of this question, which is, what about adjusting GP by the amount of light? And that's a question that comes naturally to a lot of turfgrass managers because they realize that light has an effect, as does temperature. So I want to explain how this works, and I want to start by recommending a few other blog posts, a few other things to read. If you're really interested in this, please have a look at these. I put these right at the start of the blog post. I said, if you are at all interested in this topic, please make sure you've read these posts on the topic as well. And there's 4 of them that I listed. The first one is, which affects growth more, light or temperature? That's about a spring. I spent about a month in Reykjavik, near Reykjavik in Iceland. And the temperatures were close to 0 Celsius. The growth potential was close to 0. The grass was completely dormant. The grass was not growing. I also brought a photosynthetic photon flux density meter with me, and I was making measurements almost every hour on sunny days to check how the photosynthetic light was changing through the day. And if you add together all of those measurements, you get something called the daily light integral, or DLI, which is the total amount of photosynthetic light that was available to the grass over the day. Or not available to the grass, it's what actually impacted or reached a surface of the Earth's surface. That's what the DLI is reporting, and it's on a per square meter basis. So the DLI in those conditions in the spring was almost perfect for cool season grass. On sunny days, it was something like 50, but the grass was completely not growing because temperature was totally limiting the growth. And what I find is that temperature often is the controlling factor in how much the grass can grow, and the light usually is not. There's usually enough light. There's usually conditions where the temperature varies to affect growth, and light is not varying that much. I also wrote about combining light and temperature in a post called a DLI index, and I looked at zoysia coming into and going out of dormancy in the winter and answered a question someone had asked me. They asked, is it temperature that affects that, or is it the day length? And I concluded that it's temperature because day length in this case would be a proxy for the photosynthetic light. I concluded it was temperature because, the day length moves together with temperature in temperate locations. As you move away from the equator, what you find is when the temperature goes up, you get more light. When the temperature goes down, there's less light. It turns out that there's still quite a bit of photosynthetically active radiation, even in the winter. I've got another blog post that I suggested looking at that is PAR looks like this. Photosynthetically active radiation looks like this. And I showed how it changes through a day and how it changes through a week, how it changes through a year. And it never gets to 0. It never gets to the point where there is no light. The only place where that would happen is at the North or South Pole, or places inside the Arctic Circle, I believe. Whatever latitudes north and south it is where you get complete 24 hours of darkness, those places would not have photosynthetically active radiation for some times of the year. But in most places where turfgrass is grown, the light never actually gets as low as people might expect, but the temperatures are so cold that the grass can't grow, there still might be enough light to support good growth. And I remembered that I'd written an article about this a couple of years ago for the column that I write each month in Golf Course Seminar Magazine, which is a magazine that's published by Golf Digest Japan. And I looked this up, and then I said, let me share this in the blog post. I think this might help to explain to some people who have an interest in this topic. So I wrote in this blog post, I said, I've also written about this in my column for Golf Course Seminar Magazine and have made calculations and explained them in those columns. The remainder of this blog post will be excerpts from a couple of those columns. I looked up a figure that I had prepared that has a title of Actual and Potential DLI, Daily Light Integral. And this was calculated for January 1st, 2021 at Osaka. I can get the DLI information from the Japan Meteorological Agency. So I could look at what was actually measured by a sensor in Osaka. And then I can calculate what it should be, because there are equations that one can use, because the astronomers have figured out the location of the Earth at any known second and the location of the sun at any known second. And there's an astronomical constant, or a solar constant, of how much energy on average will be reaching the top of the atmosphere from the sun. And based on the latitude and the longitude and knowing the exact location on the Earth's surface, if you then go up to the top of the atmosphere, immediately or directly above that point on the Earth's surface, you can find out how much solar energy, how much light will be reaching the top of the atmosphere at any second on any date for any location. And then on a clear day, when there are no clouds, generally you're going to get about 75% of that radiation will pass through the atmosphere and reach the surface. So you're able to calculate what percentage of that light is in photosynthetically active wavelengths, and then you can get a DLI based on knowing the location and knowing so you know the location on the Earth's surface, and you know the time, and you know the date, and then you can make all of these calculations. So that gives you your potential photosynthetic photon flux density for every second of that day. And if you add all of those together, you get your potential daily light integral. That's the maximum amount. And that's based on a clear day. In fact, I have an app, a Shiny app that calculates this. I will put a direct link to that in the show notes also. So if you are interested, wherever you are in the world, if you're interested in finding out what your maximum DLI on a sunny day would be, you can check that out. And it will also tell you for any time of day what your PPFD would be on a clear day. And so we've got two things. We've got what your actual DLI is, and then we've got your potential DLI. And that gives you something that can be expressed on a percentage basis, which is kind of similar to the growth potential. Growth potential is on a scale of 0 to 1, or if you prefer, you can call that from 0% up to 100%. That's how growth potential works. And if you take your actual DLI and divide it by your potential DLI, then you also get something that is on a scale of 0 to 1, or if you prefer, that would be on a scale of 0 to 100%. I wrote in this chart, I said, adding together the photosynthetically active radiation, PAR, for each hour produces the daily light integral. On January 1st, 2021, that's the date where I made these calculations, as an example for this article. On January 1st, 2021, the actual DLI was 22.4 and the potential was 26.2. That's in units of moles of photosynthetically active radiation per square meter per day. And this gives a DLI index of 0.85 or 85%. So now we've got a light index that's on the same scale as growth potential. It's 0.85 and growth potential it's 0.85 or 85% for this particular day in Osaka. And you could calculate your DLI index for anywhere. So that is interesting because now we're making some progress in being able to consider GP, the temperature-based growth potential, and the effect of light on a similar type of scale, on the same scale, on a scale of 0% to 100%. So it seems like maybe that is going to be useful, but actually, as I've worked through it, I've found it's not so useful after all, because this is the middle of winter. And we need to consider the scale of the numbers. January 1st, okay, it's early winter, but it's just after the shortest day of the year. It's a time of year when there's not very much light, but the actual DLI was 22. The potential DLI was 26. If that's as low as it gets in Osaka, that's not very low, because if you look at the research from Dr. Mike Richardson and I think Travis Russell was the graduate student doing that project at the University of Arkansas, they found that in the summer, bentgrass did just fine with a DLI of 30. So we're talking about a shortest day of the year. You know, we're within 2 weeks of the shortest day of the year, and the actual DLI is in the 20s. And so it's pretty close to what would be an optimum DLI for creeping bentgrass. So it's like it's not limiting so much. And that really is the main thing, that the temperature varies so much that the temperature will really have a huge effect on how much the grass can grow, on how much the grass will grow. But light just doesn't vary that much. It varies, but it never gets that low. So let me scroll through. I'll look at some of this, of what I pasted in here. Let's see. Most of this, I chose the quotes that I think are quite general. So let me read some of this for those of you who haven't seen the blog post or who would like to hear me read it and highlight some of the points that I would like to explain further. So this is quotes from the articles that I wrote in the column in Golf Course Seminar magazine. I've used this light index, which I've called a DLI index, as a way to adjust the temperature-based GP by the amount of photosynthetic light. To calculate the DLI index, I find the DLI for a day and put that in the numerator. And I also find the potential DLI for that same day and place that in the denominator. Remember, I explained how you find the potential DLI. You use some calculations to find the amount of light that would reach the surface based on what would reach the top of the atmosphere on that day at that time for any latitude and longitude point. The resultant DLI index is a number that will also be on a scale of 0 to 1, where a low number means the amount of light was low compared to what was possible, and where a high number means the maximum possible amount of light reached the grass on that day. Does that make sense? There is some maximum possible amount of light that can reach the grass, and that depends on the location and the time of year. I then mentioned Sydney, Australia, and Osaka, and of course it being different because of latitude. It would be summer in Sydney while it is winter in Osaka, and so on. So I talked about that a little bit, and then I said the result of this is a measured DLI of 22.4 moles per meter squared per day on January 1st in Osaka on January 1st, 2021, and a potential DLI of 26.2. Dividing the actual DLI by the potential DLI gives the fraction of light that reached the grass, 0.85. This is what I call the DLI index. When people ask me about the effect of light, this calculation that includes actual and potential light is what I recommend. And now we're going to get to the part where I've been excited about this calculation and thinking, okay, I'm going to figure out how we can integrate these. But now we're getting to the part of the calculation where I despair of combining them and just realize, wait a second, the light doesn't have as much of an effect as I might think. So quoting from the article again, but I also go back to the temperature, because when it comes to growth in Osaka on that January 1st day, the light was quite good. That's quite a substantial amount of par for cool season grasses. However, the low temperature was 2.3 degrees Celsius and the high was 7.6 degrees Celsius with an average of 4.6 degrees Celsius. The temperatures are so cool that I don't expect much growth at all. The cool season grass GP on this day was 0.02 or 2%. As one goes through the year looking at light and temperature, I keep finding that although light is interesting to consider, I think temperature is more important. I guess I just want to suggest work through the calculations, and I think you might be surprised at how much light there is that reaches the turf. The cool season grass actually has a light saturation point in midday of about 1,000 micromoles of photosynthetically active radiation photons, about 1,000 micromoles of photons of photosynthetically active radiation per square meter per second. And full sun in summer is about 2,000. So cool season grass can only use about half the available light anyway. And if you work through the calculations like that, then what you find is even in winter, there's often, basically in most places where there's a big population on this planet and where there are where there's turf grass, and where we're not dealing with turf inside a stadium in Stockholm that is shaded, or we're not dealing with turf in a stadium in Kashima, Japan, that in the winter the light from the sun doesn't reach the grass because of structural shade. But if we're just talking about out in the open where the grass is not having structural or tree or mountain causing shade, there's more light in the wintertime than you might expect. And so light just can't be as limiting as people might think. And if the light cannot be limiting, then I don't really see how it can be included with the growth potential based on temperature when the temperature itself is completely limiting. I then wrote another column about this, so I skipped to that, and I said, let's see, table 1, and I'm referring to the column in the May 22 issue of the magazine. May 2022 issue of Golf Course Seminar magazine has that table. Table 1 that shows the monthly averages of temperature-based growth potential and DLI, and the various DLI indices and growth indices. So if you multiply the temperature-based growth potential by the DLI index, then I would call that a growth index. I calculated that for Osaka in 2021. If one wants to consider both the effect of temperature and light on how the grass has the potential to grow, this is one way to do that. At Osaka in 2021, the C4 warm season growth potential ranged from a minimum of 0 in January to a maximum of 0.89 in July. The C3 or cool season grass GP ranged from a minimum of 0.07 in January to a maximum of 0.93 in May. The temperature, as you can see, goes down to a level where it can basically stop grass growth, and up to an optimum level at which there can be maximum growth. That matches exactly what one sees for actual grass growth in the temperatures of Osaka. But that's not what one sees with PAR. And I'm referring here to what's in the tables. I said, notice that the DLI index and the adjusted C3 DLI index, that adjusted C3 DLI index is accounting for the light saturation point for cool season grasses, are confined, these DLI indices are confined to the range of about 0.5 to 0.8. I would understand that to mean that there is usually from 50 to 80% of the light the grass can use, depending on the season. But temperature can vary so much that it completely controls, it stops or allows growth. By multiplying the DLI index by the GP, the resultant growth index shows the GP after adjusting for light. And what I find is you get almost the exact same curve after you adjust that for light. You get the exact same curve as you do when you look only at the temperature-based GP and that curve. So then going back to the blog post, I said, my take-home message at this point, after reviewing a lot of the calculations I've made and reviewing a lot of my writing about the adjustment of GP by light, is this, : although it seems like a good idea to adjust temperature by light, for C3 grasses, temperature is often a limiting factor for growth. Light rarely is. I would encourage those interested in this to work through the calculations, and I think you'll come to a similar conclusion. That doesn't mean light should be ignored. I recommend considering it as part of an environmental productivity index that incorporates nitrogen, light, water, and temperature. But temperature on its own and GP on its own does surprisingly well at describing growth potential. That is the blog post, and so I'll put a link to that. I'll put a link to the photosynthetic photon flux density calculator. I'll put a link to that book by Park Nobel, and maybe a couple of those articles by Park Nobel in which he describes the environmental productivity index, and maybe I'll even track down a couple of my old sets of presentation slides where I have showed some of that. I guess maybe some people are concerned about growth potential in tree shade, growth potential in structural shade, and so on. And I'm just not so excited about using growth potential in that situation. When you're dealing with severe shade problems, I'm not really sure that you need to use growth potential at all, because in the cases where you have severe shade, where you just don't have enough light, that then becomes the factor that you need to consider, and you just need to either remove the source of shade or you need to supply supplementary light. So I don't really see where getting into growth potential and combining that with light is really going to be very useful. I think for me the idea would be just focus on supplying enough light. But so I'm not really considering stadiums here, and I'm not really considering those type of golf course tees or golf course greens that are in those shaded pockets and they don't get light, or there's a mountain that's blocking the sun in the winter and they don't get light for 2 or 3 months. I'm I'm not really considering those because I consider them to be special cases, and I don't really consider the routine use of growth potential, even the temperature-based growth potential, to be terribly useful in those kind of situations. Maybe I'm missing something. So if I'm totally missing the point here, please let me know and tell me why you still want to combine these and how that could be practically useful. But my consideration of the topic usually involves looking at areas that are not really affected by heavy tree shade, areas that aren't inside a stadium, and just looking at turf on the Earth's surface. And if we then look at temperature and we look at light how it changes through the year, the temperature generally changes quite a bit, and the amount of photosynthetically active radiation might not change as much as you think it does. And that is, as far as what the grass is seeing, I think the grass's growth largely is getting controlled by temperature. So this is an interesting one. After I posted this on Twitter, and the Pace Turf account retweeted it, a couple of people, Paul Luby down in Cairns, Australia, wrote and said that he's seen some grass declining in quality going into autumn as the light, as the amount of photosynthetically active light goes down. And I think that's interesting because I wouldn't expect the amount of photosynthetic light in Cairns to go down by that much from summer to winter. And the temperature will also be going down too. So if you have the temperature and the light moving together, then I think we have to consider, if they're linked together, we have to consider which one is actually having the effect. So I promised Paul that I would make some more calculations of that. I have not done it yet, but it's something that I'm going to continue looking into because I am fascinated by this light issue, and in understanding the growth potential and understanding the ability of the grass to grow in different conditions. It's an interesting topic, and I am glad that people have so many questions about it. It's just I've written various blog posts about it where I've showed specific examples where the light was definitely not limiting, but the temperature was. And just the way I'm looking out the window now, I'm in Hokkaido, Japan. I'm looking out the window and there are piles of snow outside. And in fact, I'll calculate what the DLI is here. I'll find a nearby sensor and calculate the potential DLI and the actual DLI and maybe share that in the future. The grass is not growing. The temperatures are below zero at night. I've been here for about a week, and the temperature has been below zero at night, every night, and it's been just above freezing, just above zero during the day. I think the average air temperature each day is probably below zero. The growth potential will be zero. Not only is the grass covered in a lot of snow, the grass is also, it's not growing. And even if the grass wasn't covered in snow, it would not be growing. So for me, that is the temperature that is completely limiting the growth. And I keep seeing that. I've seen it in Iceland, and I see it in Hokkaido, and I see it in other places where I make this calculation. And to me, it just seems that although we want to think that light has a big impact, it does have a big impact on the quality of the surface. But as far as growth goes, I think temperature has a much bigger effect. And so because of that, I haven't really seen an easy way to integrate these, because the temperature just seems to have the dominant effect. And I guess for light, I kind of talked my way through this and remembered something that I thought is that maybe that DLI index, the amount of actual light compared to the potential light, could be some kind of stress index. Because if you're constantly running at half the amount of light that there could be, that could be like a stress index for light. So maybe that would be like a something that could be useful somehow. I guess I can look into this also. I have some promised calculations to make for Florida also, about what the amount of light was during the winter last year, or even going into this year, where they had the El Nino weather pattern and it was more cloudy than usual, and the daily light integral was considerably lower than usual. And so I've got those calculations to make too. So maybe rather than rambling on this podcast, I will get to writing and get to calculating and get to data downloading and see if I can come up with some more interesting information about the daily light integral. One more thing, I've had a few people mention to me from all around the world that they really enjoy Travis Shaddix's podcast or videos. That is, I believe that's the Turfgrass Epistemology channel. And if you haven't checked that out, you might like to do that, because he's talking about a lot of turfgrass science issues and a lot of turfgrass research that some people may not be so familiar with. And then Travis is highlighting some interesting articles and some interesting research findings, and then talking about them in quite a bit of detail. So I suppose that it's something kind of like a graduate level seminar on turfgrass research findings. And for some people around the world who are watching this or listening to this, you may also enjoy Travis's podcast. I think he offers that as a podcast and as videos on his YouTube channel. So I can put a link to that also. And I know some of the people who listen to this have told me that they enjoy that. So I will mention that to everybody. And you can check that out and see if you like that kind of content also, to learn more about turfgrass. All right. That's about all I have for this episode. So I will sign off now and promise to be back again before too long with more interesting turfgrass information for ATC from Hokkaido, Japan. I'm Micah Woods. Bye-bye.